Let's now turn to use of supernovae as a standard candle to measure distances in cosmology. This is today one of the most powerful tools in the observational cosmology arsenal to measure distances over cosmological scales. We keep using the term standard candle, and this is where it comes from. Actually, there used to be such a thing as standard candle, and such standard candles ostensibly had the same brightness. Now, a supernova is a lot brighter than a candle, but the same concept applies. So if somehow a supernova or something else has a constant luminosity, if we put it at different distances from us, its brightness will decline according to the inverse square law, or rather the relativistic version thereof. So if we can measure relative brightness of the standard candle at two different distances, we can derive what's the ratio of their luminosity distances. Similarly, if we have objects of a standard size, like a ruler is always the same size, and observe it at the different distances from us, the ratio of the angular diameters will be equal to the ratio of the angular diameter distances. So we could use standard rulers to determine the relative distances to objects we're looking at. So how do supernovae play in this? They're certainly very bright, can be seen very far away, which makes them useful for cosmological tools. And turns out they can be actually standardized. Now there are two different kinds of supernovae, and both can be used, although one of them is much more useful than the other. First, they're so-called supernovae of type 1a. They correspond to detonating white dwarf stars, which have accreted too much material for their own good, either from their companion or by merging with another white dwarf, which causes instability and explosion. They're pretty good standard candles already, and they can be made even better using a trick that I'll show you. We use their light curves, brightness as a function of time, to put them to a standard. The other type of supernovae are type 2. Those are very massive stars that are at the end of their life and explode because their core collapses. Now they have a much larger spread of luminosities, and that would not make them good standard candles. However, they can be used in a slightly different test called expanding photosphere method, which is similar to the Bode-Wesseling method that we mentioned earlier when we were talking about pulsating stars. And thus they can be used as an independent check to those measurements made with supernovae of type 1a. So here is schematically shown the difference between average light curves of the supernovae of two kinds. In both cases, their brightness increases as the star explodes, and then declines. The shape of the light curve is different because it's powered by slightly different physical mechanisms. Supernova classification is actually a little more intricate business. There are these two basic channels, either massive stars at the end of their life that exploded because they no longer produce nuclear reactions in their core, or white dwarfs that are pushed over their stability limit by an additional accretion. They come in many different varieties, in terms of spectra and so on, but there still are these two basic mechanisms, although they can manifest themselves in a broader phenomenological sense. So type 1a supernovae are believed to come from detonating white dwarfs, and I'll tell you why that is in a moment. A white dwarf is a low-mass star that has shed its envelopes. It's at the end of its life. Its core is just slowly cooling down. They're not making energy on their own. There are no thermonuclear reactions in their core. But sometimes, or often, they can be in binary systems, since the majority of stars are in binary systems. And if the binary is close enough and their companion is not yet a white dwarf, the gravitational field of a white dwarf can pull the outer envelopes of the companion and accrete on the surface of it. Once the mass of the white dwarf crosses the so-called Chandrasekhar limit, which is the highest mass a white dwarf can have, and be stable against collapse due to the degeneracy pressure, the star explodes. Another way of dumping more matter on it is if there is a binary white dwarf and they lose energy by emitting gravitational waves and spiral in. As the two stars merge, you get something that's twice as big as then what's sustainable as the two stars merge. The effect is the same. So we're pretty sure that type 1a supernovae come from detonating white dwarfs, although this is not yet 100% certain. The reasons why we think this is the case is as follows. There are no hydrogen lines in the explosions of type 1a supernovae, meaning they have shed all of their envelopes, so it has to be an old stellar remnant, which would be just like a white dwarf. There are also strong lines of silicon, which means that nuclear burning in the progenitor has to have reached at least that stage. Second, they are seen in all kinds of galaxies, elliptical as well as spiral. Young massive stars that are responsible for type 2 explosions are only found in star-forming regions, that is, like disks of spiral galaxies, but not in old stellar populations like bulges or ellipticals. Type 1a supernovae are seen in all environments, so they have to come from some kind of old progenitor, and white dwarfs fit that bill. Furthermore, they do have remarkably similar set of properties, unlike type 2s, which suggests that there is single progenitor mechanism. Their light curves are powered by the radioactive decay of an isotope of nickel. It's about 1 solar mass worth of radioactive nickel. However, this is an explosion of a whole star, and that by definition is a very messy business. We can model supernova explosions in supercomputers, but that is still not a perfectly well solved problem. This is a very complex phenomenon of nature, and you can imagine it will be kind of hard to standardize an explosion. So how is it possible that these are standard candles? There is an empirical relationship between the shapes of light curves of these supernovae and their peak luminosity. And it goes in the sense that those that are intrinsically more luminous are also slower in decaying. Since the light curves have similar shape, they can be parameterized by a stretch factor. One can be stretched into another, and then they can be shifted vertically. When you do this, the following happens. Here we show on the top a set of actual light curves of some type 1a supernovae, and the second panel shows what happens when we normalize them and correct them with the stretch factor. Suddenly, they all seem to fit this one universal shape. It turns out that by doing this, we can standardize the peak luminosity of a type 1a supernova to 10% or even slightly better, which is plenty good enough for cosmological purposes. Note again that we have to calibrate this standard luminosity using distances to galaxies that are measured in some other way, say with Cepheids. There aren't very many of those, maybe 20 or so, that have both Cepheid measurements and supernovae. A very similar result can be obtained by looking not only at the shape of the light curve, but also behavior of different colors. The more luminous supernovae tend to be decaying slower, but also have systematically different colors. Either way, supernovae of type 1a can be standardized so their peak brightness is nearly constant to within 10%. And that's what makes them really useful as cosmological tool, not just for the measurement of Hubble constant, but also other cosmological parameters. And for example, they have played a key role in the recent confirmation of the existence of the dark energy. Here is an example of a supernova 1a Hubble diagram corrected for the stretch factor and so on. The scatter is remarkably small. What's plotted here is the distance, luminosity distance in form of distance modulus versus the redshift. And it is as good a Hubble diagram as you ever hope to get. Now, the other kind of supernovae, type 2s, can still be used with a different trick. This is a so-called expanding photosphere method. An interesting thing about this method, it's based on physical reasoning and in principle does not require messy calibrations. However, it is model dependent and that more than compensates for the other benefits. It is very similar in principle to the Bode-Wesselink method we used for pulsating stars. This uses type 2 supernovae, and it can be cross-checked with Cepheids to see how well it works. The physical basis behind this method is that supernova photospheres will emit light in a way that's not too different from the black body radiation, according to Stefan Boltzmann law. So if you can measure temperature, and if you can measure the radius of the photosphere, then you can immediately derive luminosity. From the luminosity and observe the apparent brightness, you can find the distance. So this is how it works. The angular diameter of the expanding photosphere is the ratio of its physical diameter and the distance. And that can be folded through the Stefan Boltzmann formula as shown here, except that there is an extra fudge factor that's inserted to account for the deviations of the real supernova spectra from the black body. This is where theory comes in. That's where the modeling comes in. Just like with Bode-Wesselink method, We can figure out the radius from observing the velocity of the expanding photosphere from the moment of the explosion as a function of time. It is probably as good approximation as any to assume that the initial radius is about 0, because it is certainly much smaller than radii of the expanding supernova shells. Now we have everything we need. We can simply solve for the distance. But again, there is model dependence. An expanding shell of a stellar explosion is not exactly in equilibrium, and its spectrum is not exactly that one of the black body. So modeling has to be done in order to connect the two. Next, we will talk about what was really the first definitive measurement of the Hubble's constant using Hubble Space Telescope.